Hello everyone, welcome to section 5.2, matrix solution of linear systems. So we've talked about linear systems a little bit in the previous section. We used some substitution and elimination to solve those. And now we're going to look at another method which will allow us to solve this. So what we're looking at today is going to be using a matrix, or plural matrices, to solve a system. And so a matrix is another way to organize the information stored in a system in a way that's convenient to do some computation with. Okay, so let's take a look at converting a system into a matrix. Okay, so here we've got a three variable system on the left, and it starts with x plus 3y plus 2z equals 1. And you can see to turn it into what we call an augmented matrix, and the augmented part is that we have the part after the equal sign. And in order to do that, we basically take the coefficients from the left side and rewrite them as just those values in this rectangular table. Okay, so we have 1x, and you can see in the first spot I've got a 1, 3y, and in my second spot I've got a 3, 2z, I've got a 2, and then of course 1 being the last number there, what it's equal to. So that vertical line is completely optional, but it basically represents our equal sign here. And this again is referred to as an augmented matrix because of that section after the equal sign. So if you did not have that 1, 2, 2 in the last column, we would say, hey, that is going to be a normal matrix versus an augmented matrix. Okay, so most of what we're going to do is relying on augmented matrices. Okay, and now we talk about the dimensions of a matrix, and they're always written as the rows by the columns. Okay, so this one we have 3 rows, okay, and 4 columns. So we would call this a 3 by 4 matrix, right? So 3 rows and 4 columns. Okay, so what is the purpose of this? Well, a matrix kind of makes things convenient to compute, and especially for computers and calculators. Using matrices by hand, while useful, is not the most convenient thing because it's kind of like doing elimination on a system on a larger scale. Okay, so let's take a look at what we can do with matrices first. So some transformations, some ways we can manipulate this matrix. So first, we can switch any 2 rows around. And that's basically saying that the order of these 3 equations that are in our system does not matter. Okay, we could flip them completely in the opposite order and it would not matter. Does not matter which row you put first. Okay. We can multiply or divide the elements of a row by any non-zero number as a constant, okay? So basically, if you have an equation and you multiply every number by 2, that equation remains true, okay? So that's basically number 2. And then number 3, you can add or subtract a row from another row and use that in that same spot, okay? So you could take the first row and subtract it from the second row and keep that as one of your rows, okay? So, and that's kind of using that adding and subtracting method is going to let us eliminate variables and solve these systems, okay? So let's dive a little bit deeper into this. And so we're going to look at what they call the Gauss-Jordan method of solving systems. Okay, so Gauss is a super famous mathematician, one of the most gifted that we've seen in a long time. He worked on a lot of stuff, and people were dragging him around all over Europe to try and come work for their universities. Okay, so this technique basically has a goal, which is to get our diagonals to be carrying the number 1. So everything else should be 0, and along the diagonal, we should have 1s. So why is that helpful? Well, let's translate this back into an equation real quick. So this first line would read as x equals to a, and y equals to b in the second line. So in this case, it would be like x equals a, y equals b, and z equals c, right? Note that in each case, x, y, and z are going to always be in those columns, and then what they equal is in the right-hand side. Okay, so you can see that in this diagonal form, or as we call it, row echelon form, we have now solved what these variables are. Okay, so this term reduced row echelon form is super important to remember. It is one that comes up a lot, and sometimes people shorthand it as RREF, reduced row echelon form. Okay, and so again, once you have the equation in this form, you've basically got your solutions here, right? Because we've got x equal to a number, y equal to a number, and so forth. Okay, so what is the Gauss-Jordan method? Okay, so it says first we should take the first element of the first column and we need to turn it into a 1. Okay, so they've kind of outlined these steps for us. Let's go through it. We'll show you a basic example, but we're not going to dive too deep into this. Um, we'll just understand the tools and then we will see how a calculator will allow us to solve this pretty easily. Okay, so first, let's take a look at our example and let's turn it into a matrix first. Okay, so in our matrix, we'd have an augmented matrix, and it would be like 3, -4, 1, and 5, 2, 19. Okay, so this would be my matrix. And from here, my first step should be to make the first element into a 1. So this 3, I need to turn it into a 1 somehow. And the easiest bet for this is going to be to divide that entire row by 3, or multiply it by 1/3 if you prefer. Okay, so what I'm going to do is step 1, I'm going to do R1, and I'm going to divide it by 3. Okay, so if I take row 1 and I divide it by 3, my matrix looks something like this now. Okay, 1, -4 over 3, and I've got 1/3, and then we still have the second row being the same, 5, 2, and 19. Okay, and so that's the first step, getting this first number to be a 1, right? So by doing this, we've taken the first step to getting into our reduced row echelon form, and that's gonna kind of get us a step closer to our solution. So then let's take a look at step 2. So step 2, we're saying, can we use that first row to turn all the rest of the numbers in the first column to 0? So basically, I want to somehow cancel out the 5 that I've got here. I want to somehow get rid of that. Okay. So what we're going to do is we're going to take the second row and I'm going to subtract 5 of the first row from there. So basically you multiply the first row by 5 and subtract it out of the second row. Okay. And when you do so, okay, you are going to get something where that first number is 0. Okay. So our matrix now looks like this after completing this step. So 1, -4 over 3, 1/3, and we've got 0, 26 over 3, and 52 over 3. Okay, and of course, you can see these numbers are not necessarily the prettiest, but if you look at this first column, you're going to notice that, hey, we are making some progress here. Like these are becoming closer to what we want, right? And so now, like, what should I do from this point? Well, we want to now turn this into a 1, right? So by turning this diagonal into a 1, we're going to do R2, and we're going to divide by 26 over 3. You can also multiply by 3 over 26. It's the same meaning, right? And let's see where we're at now. So this matrix is going to look a little bit nicer, but not necessarily at our final product. Okay, 1, 0, 1, 4 over 3, and 2. Okay, so interestingly enough, now we're almost to our row echelon form. We've kind of got the diagonals going the right way. We've got those ones, we've got the 0 in the right spot. So the only place I need to fix is now this one, right? And so basically, we're going to use that second row where there's only a 1 there, and we'll subtract it from the first row. So we'll do something like uh, R1 plus 4 over 3 R2. And so you can tell, like, hey, I know since it's a 1, I know that if I multiply by 4 over 3, it'll cancel out that other piece. And when we do, we're now going to end up in our fully reduced form. So this will be kind of my final form. So we've got like 1, 0, 0, 1, and you should get this is going to be 3 and 2 is what we come up with there. Now, I didn't spend a lot of time doing these computations, mostly because it's a little bit arbitrary. We all know how to multiply, we all know how to add, subtract. It's just kind of tedious to do so with all these fractions. So, how is this method considered to be efficient, right? I'm pretty sure I could have figured out x equals 3 and y equals 2 much faster and much cleaner by using something like elimination or substitution in this case. It would not have been hard for me at all if we used the second equation to eliminate y from the first equation, and we'd have gotten something that we could solve for x with. Why go through all this trouble of doing a matrix? And no, it's not just to make your life difficult. It's because as you expand and add more variables, the power of matrices kind of shines through and becomes more relevant to us, right? And now the actual expectation is because this method is so simplified in how to do it, right? Each column, you're going to do this. You make the first number a 1, then you use that to cancel out the other rows. Then you go to the next one. Then you make row 2, column 2, make that into a 1, proceed the same way. Repeat, repeat, repeat. And since the steps are so repetitive, computers excel at repetitive processing. And so we can calculate matrices that are hundreds of variables in length to help us optimize and calculate combinations of things and figure out what is the best case scenario in very short periods of time rather than trying to do it by hand or rather than trying to create a elimination method. Because if you program a computer to do algebraic elimination, it essentially is going to be working like if you're in a matrix, right? So anyone who's interested in computer programming, you will see matrices a lot. As for the rest of us, we're going to kind of now rely on the calculator for the most part to solve these, okay? So let's take a look at one more and check out another solution here. Okay, so here we've got a 3-variable system, and we're going to solve it using a matrix with our calculator, okay? And so let's go ahead and set this up as a matrix. And so we've kind of got 3 rows, and we're going to have 1, -1, 5 equals to -6, 3, 3, -1 equals to 10, and 1, 3, 2 is equal to 5. And there we have it. That is our matrix. Okay, so now let's talk about how you can put this in the calculator. And what you're going to do is if you're using a TI Inspire, it's pretty easy. You just have to go to the menu and we're going to access the matrix menu. Now, most modern graphing calculators have some kind of matrices option. And so even if you're using an older one or a different brand, you should be able to find these same options. Okay, so what we're going to do on the Inspire, we would use menu 711, okay? And that is to create a matrix, okay? So it's going to pop up and it's going to ask you what dimensions you want. So again, this is a 3 by 4 matrix, okay? So 3 rows, 4 columns, okay? And what you're going to do from there, you're going to enter all your numbers in there, and it pops up with like the matrix and then a little arrow, okay? So what you're going to do here is you're going to put in the name that you want for your matrix. Usually people put like whatever letters you want. You can call it matrix A, matrix B, matrix C, matrix Paul, Peter, whatever you want to name it, okay? And then you are going to go back to that same menu and you're going to go to menu 7 and then 5. So menu 7, 5, and you're going to do like, it's going to pop up with this RREF, and in here you're going to put the name of your matrix. And once you do, you push enter, and it's going to pop out with the reduced row echelon form, and it's going to basically spit out your answer for you here. So you're going to have something. And that is your matrix in its reduced row echelon form. And that, of course, is going to be the solution to your system, right? So what did we find from this system? We've got x equals 1, y equals 2, and z is going to be equal to -1, okay? So those are, of course, our solutions going down the rows in order. Okay, so menu 711 will create a matrix, and then menu 75 will reduce row echelon form that matrix. So you just have to be careful about putting in the dimensions, and you'll be able to solve it. So again, this is with the TI Inspire. If you use a different brand, there is very commonly some kind of matrix option in there to generate matrices and do all kinds of math with them, but for now we're just sticking to that reduced row echelon form. Okay, let's take a look at one more system here, and this time we're going to talk about what an inconsistent system looks like. And so if you take this matrix and set it up and let's put it in the calculator, let's see what it spits out for us. So here is my matrix. Again, if you use the calculator and you go ahead and say, let's find reduced row echelon form of this matrix. Again, that's the menu 7.5 after menu 7.11. Okay, so in reduced row echelon form, we get this 1, 1, 2, 0, 0, 1. And now suddenly I'm very confused by what this matrix says. And the confusion really comes from this second line. So first of all, it didn't give us a proper diagonal in this one. We ended up with 2 ones in the first row and then 2 zeros in the second row. So it's very strange. Let's take a look at what the equations say. So the first equation reads like this: x plus y equals 2. Okay, fine, sure. Nothing too exciting there. The second equation reads like this: 0x plus 0y is equal to 1. And you may already be like, wait, something's weird here, because this is basically saying what? 0 is equal to 1. And that is 100% incorrect, right? So basically what we've taken from this is that this is not going to work as a system solution. And basically what we're getting at is this is an inconsistent system with no solution. Okay, so that double zero situation that we ran into in the second row, that is kind of showing us that, hey, there is no solution to this. Okay, so we got one last example using Gauss-Jordan method. And so this is a system with infinite solutions. Now, I can tell you this has infinite solutions before we even get into the problem. And that reason is because you might have already noticed that this has 3 variables, but only 2 equations. And so that kind of jumps out already as kind of an alarm. If you have more variables than equations, or constraints sometimes as we call them, there are infinite solutions. There's multiple combinations that you can use to make this work, okay? But we're going to find an algebraic expression for this, and we are going to use z as our arbitrary portion of it, okay? So basically, we're going to give our answers in terms of z, okay? You could do it in terms of any of the variables. We're going to do it in terms of z, and conveniently enough, our calculator is going to spit it out in that form as well, okay? So here is my matrix, all right? So this will be what we menu 711 to create, okay? And we're going to have 3 columns and 2 rows. So 2, -5, 3, and that's going to be 1, and then we're going to have 1, -2, -2, 8. Okay, and so let's go ahead and also reduced row echelon form this. Okay, and when we do, it's going to spit out for us something that looks like this. 1, 0, -16, and 38. Okay, and the second row is going to be 0, 1, -7, and 15. Okay, and so let's turn these back into equations real quick. We've got x minus 16z is equal to 38, and y minus 7z is equal to 15. Okay, and try as you might, there's no way for you to simplify this any further and say like, hey, I can cancel another variable out. Instead, let's get our x and y by themselves, right? Solve for x and y. Okay, so basically I get something like this. X equals 16z plus 38, and y equals 7z plus 15. Okay, and so now that I've got this, let's write our solution set out. So my solution set is basically all the possible combinations that I can make like this. And algebraically, we can write it something like this. So we're going to state this is a solution set. So I'll put some curly braces. And of course, it's first x, right? So in our case, x is 16z plus 38. 16z plus 38. Okay, and then next will be y. So my y's are going to be 7z plus 15. Okay, and finally we've got z. Well, z is just equal to z. Okay, and there you have it. This is our solution, basically expressed as an algebraic relationship between the 3 variables. Okay, and so once we've solved for x and y in terms of z, we can replace them. Now, again, you could do this and put any variable in terms of the other ones, right? So if I wanted to solve everything in terms of x or in terms of another variable, we could do so. But this is the easiest expression um, because each of these has z in it, and we were able to solve in terms of that. All right, so that is using matrices to solve linear systems. Again, doing it by hand can be a little bit tedious. The true power in this is that the method is very easily programmed and it's a bunch of repetitive steps. And of course, computers and calculators excel at that. And so we can use this to solve systems that are literally hundreds of variables, which would take ages to do by hand within minutes or maybe even less nowadays. Okay, so that is the power of the Gauss-Jordan method, and hope you enjoyed this video. Good luck and happy studying, guys.